privilege of sitting down. I hope you will take me as a slow fellow. Well, the Zernike system is one of those where we started scratching on the surface some 2 years ago. I managed to interest George Bogdan, who is a researcher in Dubna, the University of Yerevan. Also Dr. Alexander Yachnu of the Department of Mathematics in Guadalajara, and Natica Tapishiev, the Institute of Mathematics in Cuernavaca, of UNAM. And strangely enough, as we started scratching this, it became simpler. It became more significant. Because initially we thought it was something about just special functions and up and down operators. But it has something behind it. So we will start out with free motion on the free sphere. The dynamics is given by the Laplace-Beltrami operator, and it's as symmetric as things can be. Then we will integrate over one of the angles so as to have a two-sphere. And we will look for coordinate systems on the two-sphere where one of the coordinates goes on the equator, on a ring. And this allows us here to give three systems that we will call system 1, 2, and 3. System 1 was given by Zernike. Systems 2 and 3 are separating coordinates for the solutions of a very specific quantum system. And elliptic coordinates I will also only mention in passing, because these are horrible functions and I don't want to scare anybody of you. So, the plan is first we start with free motion on a three-sphere. We reduce it to a two-dimensional manifold, which is actually a half-sphere, and it comes down to a circle, including the boundary of the circle, which is normally the wavefront that we get when light comes through a normal circular pupil. So the properties of this system, you will see the separability in various coordinate systems, only polynomial solutions, and interbasis expansions, which involve all or most of the higher polynomial continuous and discrete functions in the ASCII scheme. And in deriving these results from free motion on a manifold suggests that its interest is probably beyond optics. So this is Professor Fritz Zernike. He obtained the Nobel Prize in 1953. But he proposed his solutions on the disk. These are orthogonal polynomials, and they're called Zernike polynomials. They have a sort of energy index. You see 0, 1, 2, 3, 4, and so on, and something like angular momentum, -4, -2, 0, 2, and 4. So everybody would say, that's a two-dimensional harmonic oscillator. And many, many mathematicians fell into that trap and went, well, they produced papers, of course, but they didn't clarify what was really behind that. Now, just for reference, he got the Nobel Prize for the contrast-based microscopy, which allows you to actually see bacteria which are basically transparent and which do not show up very nicely when you see through transmitted light. So he made things so that you interfere these lights, but it's only marginally related to his Zernike polynomials. Now, the solution by Zernike has been used also by other people by stretching the circle or making it into an annulus or sector. How do we get that away? A ver, alguien que sepa cómo deshacerse de él. Ah, yeah. So, these things are actually used, or trying to be used, to well, take away aberrations of larger sectorial mirrors. So, let us start then with part one, which is the quantum Zernike system. Then we will see the classical Zernike system, which is also a system and also has its own solutions. So first of all, we have a very crazy operator called the Zernike operator. Now, this is a Laplacian, it's on a two-dimensional manifold. Then you have this incredible term, square, and again this one. That's a non-standard Hamiltonian. Nobody really knows why Zernike chose that one. I mean, it's in his 1934 paper. Then the following year with Brinkmann in a paper which is very, well, I didn't see it quoted any place. He relates it actually to the sphere, but we discovered that paper. But still, it's another road. And it's on the unit disk. Namely, it's on xy plane, such that x squared plus y squared is less or equal with 1. And you have boundary conditions. So first of all, you can build a Schrödinger equation. Well, Schrödinger with this, but still it's a Schrödinger equation. Here's an energy value. And you ask for the solutions to be bound. So you cannot have logarithmic solutions or singularities. They all have to be simply bound. And you find that the spectrum E, this E, is J times J plus 2. Of course, a harmonic oscillator, right? Well, no, not quite. And you get polynomial solutions. So again, we start with a three-sphere. Here we have a symmetry algebra of the three-sphere given by SO4. These are the generators of SO4, and they're given in a chain where you reduce SO4, SO3, SO2, and you can identify which generators are in each algebra. On the other hand, you can take sums and differences, and then you're inside the other chain of SO4 into SO3 cross SO3 and containing these. Now, this is the only semi-simple group that has this property of splitting. And in fact, many things that we know about Clebsch Gordan coefficients and so on come from this decomposition, namely from the two decompositions. So the Zernike system is really only making use of that. So in terms of this algebra, the algebra, we have the Laplace-Beltrami operator, which has this spectrum in a definite class of individual representations. The second Casimir is 0, identically in this realization. So these two SO3 algebras have the same Casimir operator. And then you have the free Schrödinger original free motion of the sphere system. So now, this is really the last thing we found. I would rather say it was Bogdan who found it. I just acted as a secretary, putting together all the various manuscripts and making some sense out of it. Okay, so you have the spectrum and everything is well controlled. The spectrum, the SO3s have this relation. It's the same thing when you separate the two-dimensional harmonic oscillator into radial and angular coordinates. We've probably all done that. Now, the three-sphere, where you have three angles, is a solid thing. It has orthogonal coordinate systems. These were extensively explored at the edge of the Volga by George Bogdan and several associates. These include spherical, cylindrical, spheroelliptic, oblate, and prolate, and ellipsoid. Now, we're only using that spherical, cylindrical, and special kind of ellipsoidal. But the other coordinate systems can probably give you other things. So here we have systems 1, 2, and 3. System 1 is when you have, it's the cylindrical one. You see, here you have gamma, cosine, here you have gamma sine, here you have cosine phi 1, phi 2. And the canonical spherical one is the one you usually write, namely cosine, cosine, which goes up. And here are the ranges. And the non-canonical spherical, well, you just rotate the half sphere by 90 degrees. Now, I was convinced that you would be solving that with linear D functions. So these are the three coordinate systems. And by projecting these half spheres on the disk, we will obtain the solutions we're looking for. There's a lot of algebra to be done. First of all, we want to express the Laplace-Beltrami on the three-sphere. See, here is delta in the first system, in the second system, and in the third system, in terms of the three angles. And that's the expression. We can also identify which are the sub-algebra operators that give the quantum numbers. So here we have L3 and M3 which commute. They provide the quantum numbers M1 and M2. And the solutions have three quantum numbers. And the solutions are these. Say J, M1, M2 of gamma, phi 1, phi 2. These are trigonometric. These are Jacobi polynomials in this angle. And multiplied by a phase. And as we will see shortly, you can write this as a phase, as this phase here, times a function only of gamma and phi 2. In system 2, you can do the same thing, namely you write it in terms of three angles. Here you reduce respect to SO3, L times L plus 1 as usual, and this is the magnetic quantum number L3. Okay, and the solution, well, it's trigonometrics. These are Gegenbauer polynomials. These are associated Legendre polynomials. And again, we have a phase. In this phase, we can bring out and write only the function of the last two coordinates. And the same happens for system 3. Here we have primes, and at the end, we have this phase. So, since we have these three forms of expression, I think it's easy to see that we could go from the three-sphere to the two-sphere, just here integrating over phi 1. This will give you a delta of m1 to 0. Here you integrate over phi. This puts m equals 0, and here also m equals 0. It's not mine. Okay. So here we're projecting the three-sphere on the two-sphere. And once we do that, well, there are ways of doing it. You see, you can take three coordinates, S1, S2, S3, 4 of the ambient space of the sphere, And in terms of 3 x's and 1 phi. But this means, you see, S1 is C3 cosine phi, S2 is this sine phi, and S3 is 4 are just given by x's. So all our functions of the 4 s's can be put in terms of x's, and we have always taken out the phase and remained with a function of the 3 coordinates of the ambient space of a 2-sphere. Okay, so, we check that we can, the Laplace-Beltrami of free motion of the 3-sphere equals the Zernike operator. See, plus this one, second derivative. And of course, the solution in the second derivative to find these functions is quasi-trivial. And passing from the 3 coordinates to the 2 coordinates over the disk, well, that's easy, xc1, xc2, and xc3. For system 1, we can follow this program. You see, we put the new x's with a little bar on it, not normalized. We integrate over phi1 of the functions on system 1. And we get delta m0 in the xc function over here. Well, and phase this power, especially Jacobi polynomial, here's a 0 of this angle and then a phase. Now, the indices are a principal quantum number. N is simply the 2j plus 1 of the 3-sphere, and m will be minus m2. So the coordinates are then x and y. You can write them in terms of the angles with these ranges, and specify, well, now there are eigenfunctions of this operator with this eigenvalue and in this magnetic quantum number. So you have psi1 of n, m, with indices n and m, given as in the harmonic oscillator. And so that's the that's the relation with the phantom harmonic oscillator. For systems 2, well, you do the same thing. I should say that Alexander Yachto is the computer mathematician in residence. So he's able to ascertain that all the coefficients are and all the indices are correct. For system 2, we have these Gegenbauer polynomials and Legendre polynomials. Now, these are new solutions, I would like to emphasize. The principal quantum number is now n1 plus n2, as if it were a harmonic oscillator. And there's a quantum number L now given by n1. These are the coordinates, and well, they're eigenfunctions of this and of that. And the indices are n1 and 2, where n1 and n2 plus n2 equals n. So again, we have a phantom harmonic oscillator. And for system 3, something very similar happens. Now, you will say systems 2 and 3 are just the rotated 2-sphere. But things are actually more complicated than that. And that we didn't quite know, you see. So, George Bogdan was intent on finding the overlaps between systems 1 and 2. So I told him, don't worry, these will be Wigner-D functions. Because after all, you know, the Wigner-D functions rotate the sphere, and we're rotating the half sphere. So what's the problem? Well, however, it gets clarified when we use brackets with the quantum numbers. You see, SO4 has this decomposition. Here, the subalgebra generators that give you the quantum numbers are M1 and M2, and one is opposite to the other. So our functions psi1 over here, we can write them as some normalization coefficient times the function of the previous slides. And this is pseudo basis xy with an SO3 basis given by these quantum numbers, one for each dimension. On the other hand, you have this chain, and so the eigenstates of system 2 will have n and n1 that you can rearrange as n1 and 2, normalization, the previous solution, and then this pseudo basis with n1 in the second system. By the way, Zernike and friends have studied or have introduced this pseudo basis for the decomposition for the wave functions on the unit disk. This is quantum mechanics on the unit disk. Normally when we study quantum mechanics, we're always all over space, right? The whole plane. And there are only integrability conditions that say that at infinity the function has to go to 0. Well, here we have only a compact manifold, where on the boundary we just ask the function to be finite. So it's a kind of different flavor of quantum mechanics. So, what are the interbasis expansions? Well, this is the here is 0, 1, 2, 3. The vertical axis goes with a principal quantum number. This is system 1, where here you have n1 and n2, as if it were quantums in a two-dimensional harmonic oscillator. I mean, they play the same role, but they're different. And this is a new basis for system 2 that has well, total energy and angular momentum. Now, you will note that here, this system 1, the functions on this line all have parallel lines. So it was asked at some point, when would you use one set of functions or the other? Well, if your apparatus has basically a spherical aberration, then you would use this original basis by Zernike. But if your system is misaligned, then you would use this basis, because it has all of these which correspond to misaligned plane waves coming to the pupil. And, well, I have better functions, but you can see that here we always have separating coordinates that go as the coordinates of the sphere in that orientation. So the problem of interbasis expansion is, for instance, to put each one of these 4 states in terms of each one of these 4 states. Well, in other words, these are the Zernike original functions, and you want to find coefficients such that when you sum over nm, sum over n, no, n is the same, I'm sorry, m just goes over all allowed values of angular momentum, and then you're supposed to get the new functions on the set of system 2 coordinates. So for understandability, we look for these functions correspond to this bracket. This summation corresponds to this one, and this function corresponds to this one. Corresponds to just this one. Now, here you put a complete and orthogonal set of functions in the middle, so that this becomes a Clebsch Gordan relation, which is the coupling of angular momentum half m minus a half m summing to 0. So the coefficients that we have written here as w's are given by this Clebsch Gordan relation, which can be written in the following way. You say this is angular momentum 1, angular momentum 2, projection 1, projection 2, going to total angular momentum n1, projection 0. And these are special Clebsch Gordan relations, because here's a 0. And well, this is a phase. Phases can always be attached, but we know that there's always a real solution at all. So the interbasis expansion now can also be inverted. We could check that both systems 1 and 2, if they go by W, the inverse goes by the complex conjugate of the function. So this is related to this. You just exchange rows and columns, and that's the back condition. So it's a unitary transformation between two bases of functions on the unit disk. And if we take in system 3, well, this is system 1. Here you have a phase and Jacobi. Here you have Gegenbauer and Legendre, and here also Gegenbauer and Legendre. To pass from here to here, you have special Clebsch Gordans, which are 3f2 functions of unit argument. They're also Hahn polynomials. Now, Hahn polynomials has something like 7 parameters, but these are not the most general Hahn polynomials. And the same happens here. These are 3f2 functions of unit determinant. Now, if you only want to pass from system 2 to system 3, I thought it would be just a phase of either D function, but no, it's a 4f3 function of unit argument, and it's a Raka polynomial. And it's very enticing that they're very close to 6J coefficients. This is not yet clear exactly how it comes about, but it seems to be the case. So these are the new solutions. Again, I want to point out these 3 are the same in both systems, but all the other ones are separable in these coordinate systems, which are not orthogonal, because the only orthogonal ones on the disk are the polar ones. So these are the ones for misalignment, and well, the general expression looks like this. And the quantum numbers of angular momentum and, are there. See?
What are we seeing in those plots? It is obtained?
Well, we're on the disk, on the unit disk, and the expression on the unit disk is given by this xy on the unit disk, coefficient, this power function, Gegenbauer, and Legendre.
But the distributions in those plots are the same type of phase with
they're the wavefronts of some wave field that crosses a circular pupil. Yes, that's the quantum space that we're talking here about. Now, there are also elliptic coordinates on the sphere. These are really very horrible. You see, well, there's a continuous parameter, which is the angle between the two foci of ellipses on the sphere. When you project them on the disk, they look like this. So, in one extreme, you have the polar coordinates of Zernike. On the other side, you have system 2, and this is an intermediate set of coordinate systems. And they're these because you may wonder if we ever got to plot them. Yes, we got to plot them. These are for angle of pi over 4 between the two. And you can see here the level curves go along the elliptic coordinates projected. Now, I'm almost ashamed to show you the results because they're so horrible. So you can close your eyes if you're busy. Well, these are polynomials. They're Hein polynomials in row 1 and Hein polynomials in row 2, and they're being multiplied. And well, these are results given by Mathematica. And to normalize, we didn't find a better way than just to integrate. So we have this set of functions. They're orthogonal and complete, as any basis should be. So now the Hein differential equation has 7 parameters. It looks like this, and furthermore, there are 4 families or 4 types of polynomials, and that depends whether the wave function is even or odd under vertical reflection, or even and odd under horizontal reflection. So there are actually 4 families, and well, you have to keep control over what the families are. There are 0, 0, 0, 1, 1, 0, and 1, 1. They depend on the ellipticity parameter A, and well, as functions of xi, we wrote them in terms of the Jacobi elliptic coordinates. And then there's another paper where we use trigonometric elliptic coordinates, so you can have your choice. Personally, I don't want to look at them again. So, but so you can interpolate from the Zernike solutions to the new solutions in a continuous fashion. So there's a smooth transition. Now, this is the quantum model. But there's also the classical Zernike system. Because in this case, we're going from quantum to classical. Well, what do? We have the Zernike Schrödinger equation, which was this one. Here we have 2 extra parameters, alpha and beta. Now, sorry? Yes, yes, of course, it's 4th order here, 2nd order here, and linear here. Now, this is what Zernike proposed, and I think in those days it was very elegant not to tell how you could got some equation. Anyway, several authors have said, well, to justify Zernike, you can also use other methods, like the Schmidt orthogonalization process. And so on. Now, Zernike had these two parameters, alpha and beta, And then he said, well, now we want this to be self-adjoint under the inner product over the disk. And then he found it can only be self-adjoint if alpha is -1 and beta is -2. And then he proceeded. Well, in the classical case, we can still keep alpha and beta open. So we can dequantize it in the following way. Whenever there's a nabla, we put I times momentum. It's a two-dimensional momentum. Whenever we see R, we put xy. We have this. So nabla, the Laplace Beltrami on the disk is this one, and R dot nabla is this one. So these are classical quantities, and they give us a non-standard Hamiltonian. This Hamiltonian, depending on alpha and beta, is this is comes from the Laplacian. This comes from the R dot nabla squared. This is R dot nabla, and then we can write it in polar coordinates. And here's an I. Now, Hamiltonians don't usually have I's, right? But here we have an I. And also, stranger enough, the I will eventually disappear. You see, we get a classical system where there's no I after all. And you will see. Well, what do? We use, actually, Alexander Yachno is the guy who produced the result, using the Hamilton-Jacobi equation, where we write it in this way, and then we find function S, and we separate the function, and then we put it back, and then we replace it, then put it back, integrate, replace, put it back, replace it, and then extract and alone. So we get orbits that are elliptical. Now you will say, no, that's impossible. Bertrand, with his theorem, told us that only the harmonic oscillator and the Kepler system have elliptic closed orbits. But of course, this is a non-standard Hamiltonian. So we can have all the properties it wants. Well, not all, but the one we're looking for. So, just to point out what is elliptical, you see, this is radius in terms of the angle, and it has this form. And this is an ellipse. A, B, C, D are these things. So at the end, you have this written in this way, and this is an ellipse. And there are several possibilities, because now alpha and beta are in principle free. See, we go through the process. We know that epsilon, the eccentricity of the ellipse, has to be real, which says that C is greater than 0. And there are two possibilities for the energy, this one and this one. Also, the ellipticity has to be, eccentricity has to be less than 1. This implies this restriction, and R squared has to be positive, so this gives this restriction. Now, all these restrictions turn out, if we have a diagram of energy versus angular momentum, P sub phi, these regions are forbidden, but this is allowed. And when this is allowed, you can draw the corresponding ellipses. They're all inside the unit circle, you see. However, the time differences are different from a harmonic oscillator, because a harmonic oscillator goes boom, 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 boom. Right? Well, this goes almost by equal times. So it's not a real, a proper harmonic oscillator. Now, this corresponds to, to this case. and in this region. When the region is over here, you see, when you're here, then you also have ellipses, but they're all outside the unit circle. 10 minutes, okay. So this means that we're projecting not only a half sphere, but a half hyperboloid. And these half hyperboloids can be two sheet hyperboloids. See, you have trajectories here which project to elliptical trajectories here, or two sheeted hyperboloids, where, well, we have these, and that project here outside. And they all project outside. Now, George is trying to say, well, there must be also a quantum system where we have the whole sphere, the whole plane, except for a circle. I mean, take out the circle, the unit disk, and the rest is the quantum space. I said no. I don't like hyperboloids. Now, there are some things which come up. They're constants of the motion. The usual constant of the motion is angular momentum. But separation in system 2 produces this constant of the motion. And separation system 3 produces this other constant of the motion, which depends just x, y, exchange of x, y. So out of these, we can produce functionally independent ones from the previous constants I1, I2. This is J1, J2. J3 is a Poisson bracket between J1 and J2. And this provides us a third linearly independent concept of the motion. So we have three independent constants of the motion, which is maximal for a system in 2 dimensions. So they satisfy the following Poisson bracket relations. You see J1, J3, 3, 1, 2, 1, 2, 3, as in the rotational algebra. However, J2 with J3 gives you J1 times this horrible mess. Well, no, here is a Hamiltonian, here is J1, and this is a constant. And this is not a Lie algebra, but it's a cubic Higgs superintegrable Lie algebra. Not Lie, Higgs. And you can express the Hamiltonian alpha and beta in these terms. Beta is contained in one of these two. So you can express the Hamiltonian in terms of the symmetries of the system. And the quantum operators can also have these K1, K2, K3. They also follow the same, well, actually, similar commutation relations. Oops. Well, between K3 and K2, you get this expression with a Zernike Hamiltonian here, and K1. So we have a Higgs algebra closely related with the rotation algebra. And this is muchas gracias. That is what we have been working on. So the basic stuff is that I think it's a different quantum system, right? It's not over full space, it's over compact space, yet it comes from a very symmetric system, which is this here. Just it could be a hyperboloid, a conic, and also since the 3-sphere has 6 separating coordinate systems, I think there is still plenty of special function hocus pocus that you can do and fill in a lot of papers. Some of them will be very complex, others will be hopefully more readable. So thank you very much.
We have time for some questions. Please,
I wonder if the concepts of motion that you showed us a few minutes ago, do they have some physical meaning as particular kind of variable?
Well, here they are. This is the radius, right? This is multiplied by a sort of hyperbolic momentum. It's not angular momentum, it's hyperbolic momentum. And this is angular momentum with an I. The other one, J3, just has px, py. So you can imagine that if you rotate this one, you get this one.
And those, they correspond to some quantum number in the corresponding quantum cases?
Yeah, well, angular momentum J1 is, for system 1, is clearly related. For the others, I'm not that sure how you can visualize them geometrically. In fact, say for this, well, I wouldn't know because, I mean, this is not the usual Hamiltonian. It's some kind of operator. But at the end, it's a Zernike system. And well, you have all the separating coordinates. Separability is a mark of separability. You can separate in several coordinates.
some other question? No? We thank Bernardo once again.